Okay, so this is joint work with my advisor Nishan Changotia. So let me explain the terms in the title. There are two major characters: local problem on grids and finitely dependent processes. So what are local problems on grids? So by grid, I just mean ZD, d-dimensional integer lattice. And so here is a very simple example of a local problem on grid. So can you color Z2 using 5 colors so that the adjacent colors are different? Well, the answer is yes, and it's very easy to do. So here is one sample such coloring. So whenever the adjacent colors are different, we say that the coloring is proper. So this is an example of a proper 5 coloring of Z2. So this is a solution of one local problem. So in general, a local problem on ZD is a generalized coloring problem. And instead of constraints depending only on the adjacent vertices, here we allow constraint to depend on a k radius neighborhood around each point of ZD. And constraints just specify which color patterns are allowed to appear in a k radius neighborhood around each vertex of ZD. So constraints can be something like you go at each point and you look at 10 radius neighborhood. So there are at least 7 2s or at most 5 1s or something like that. Constraints can be arbitrary as long as they are defined on a fixed finite radius neighborhood around each point of ZD. So yeah, such a problem is called local problem. And a solution to a local problem on ZD is just a coloring of ZD which satisfies the constraint at each point of ZD. So now suppose that you want to randomly generate a solution to some local problem like proper 5 coloring of Z2. Then one way to come up with solution is to define a stochastic process indexed by Z2 such that each of this random variable takes values in the set of colors 1, 2, 3, 4, 5 such that the values at the adjacent vertices are different. So if you have such a process, then the output of such a process will be a solution to this problem of proper 5 coloring of Z2. Now, if you want to do that, note that you cannot just take an independent process, because if you take an independent process, then the probability that the adjacent vertices are same is positive. So independent process will not do the job for us, but something which is approximately independent works. And so that leads me to the finitely dependent processes. So a stochastic process indexed by ZD is called k-dependent. If you take any two subsets of ZD which are separated by distance at least k, then the restriction of this process to these two sets are independent. So as long as the distance between the 2 points is greater than k, the random variables are just independent. So for example, an independent process is trivially finitely dependent because as long as the sets are disjoint, the restrictions are independent. But in a finitely dependent process, you allow dependence till some distance, and after some distance, the random variables just become independent of each other. So now, before going to the main question, I say that for a local problem on ZD, a stochastic process solves that problem if randomly drawn sample from the process is a solution to the problem. So here is the main question that we want to answer. Given a local problem on ZD, does there exist a stationary finitely dependent process which solves the problem? So this distribution does not depend on the point, vertex density. Yeah. So so of course the answer to this question will depend on nature of the local problem. So what we proved is that as long as local problem satisfies certain properties, the answer to this question is yes. So before defining what that property is, let me define some simpler property. So here is an example. So suppose you are given a proper 5 coloring of part of Z2 lattice. So here I have just drawn proper 5 coloring of a boundary of some square. Then can you extend this to proper 5 coloring of entire Z2 lattice? Well, the answer is yes, because there are 4 adjacent vertices and there are 5 available colors. You can just choose the minimum available color at each point, keep doing this, and then you can get extension to entire Z2 lattice. So whenever such a property holds, then we say that the local problem satisfies the topological strong spatial mixing. So here is a formal definition. So a local problem is called topological strong spatial mixing if any valid coloring of any subset of ZD can be extended to a coloring of entire ZD that does not violate any constraints. So for example, as we just saw, proper 5 colorings of Z2 satisfies topological strong spatial mixing, but proper 4 colorings don't. So now finite extension property is just a modification of topological strong spatial mixing, but which includes a wider class of problems. So roughly it says that if if you are given a coloring on a part of ZD lattice, and if you can extend it to some k radius neighborhood of that part, then it extends to entire ZD lattice. So here is the main statement. Given a local problem on ZD which satisfies the finite extension property, we showed that there is a stationary finitely dependent process which solves the problem. Furthermore, this process gives positive probability to all valid finite patterns of colorings which can possibly occur. And we showed that the set of stationary finitely dependent processes is weak star dense in the set of all stationary processes which can solve the problem. And if you are from computer science, then our result implies that there is an efficient randomized local algorithm which solves the problem.
There's no claim that distribution on the solution is uniform or
no.
only that it's bounded at all possible.
All possible, yeah, yeah. Yeah. Yeah, that's the thing. Thanks. Sorry.
So I ask you one thing. How does this relate to things like what is it called? Factor of IID, finite factor of IID, where you sample IID and then.
Yeah, so this process is a factor of IID. It's a finitary factor of IID.
But there you cannot even get uniform, like the distribution you want.
I mean,
but under a stronger condition.
So like if it is topological strong spatial mixing, like with very strong properties, then you can get it as a finitary factor of IID. Like the uniform Gibbs measure.
It's also a finitary.
It is a finitary factor of IID.
Yeah. But with just finitary factor of IID, you can even get stronger properties, like things like
uniform Gibbs measure or something like that. But yeah, this is not.
But with weaker, but yeah, with almost nothing, with just extension, you are getting solution to it.
Yeah.
Okay, so yeah, let's thank